Okay, today we're going to cover a couple of things. We're going to cover the one proportion z-test, and then we're going to cover sample size considerations when you're interested in having a certain margin of error. So before I go to just start working the tutorial problems, I'm going to give you just a really brief overview of the one proportion z-test. Okay, so when we're talking about proportions, the statistic is going to be p hat, the sample proportion. If you need to, maybe you can go back and review that. That was on the first test. P is the population proportion. And we're going to have to also be given some, of course, sample size and information like that. But anyway, when we do the z-test, and all of the 1 and 2 proportion z-tests, we'll get to 2 next week, are just using the z-test. So it's going to equal the statistic minus the hypothesized parameter divided by standard error. So let me just make up some numbers here. Let's say that p hat was equal to 0.44 and that the hypothesized proportion was 0.5 and that HO was, well, I already said that, p is equal to 0.5 there. And let's say that we had a sample size of 100. So that means that the number of people that said yes in our sample was 44, and that's how we ended up with that 0.44 there. So this would be the statistic, 0.44, minus the hypothesized parameter over the standard error, which is pH, that's what we had right here, 0.5. That's the proportion of our that we hypothesized to say yes, and the corresponding, the complement of that, 1 minus that, is also 0.5 in this case. That's the proportion that would say no. Those have to add to 1. Okay, so whenever you have P and Q, those have to add to 1, and then N is 100. And then you would go on and carry out your test in the normal way that we have previously. In fact, we'll see that in a minute here with a couple of problems. One other thing I wanted to say is, when is N large enough for valid inference? It's not the 15, 40, 100 rule. It's this. You have to look at your standard error, or your, in this case, we're using standard error, so it's the hypothesized, the 0.5 here. And if we had 50% of our sample of 500 saying yes, this would be 50. So if our sample size 100 and P is 0.5, we will be saying that we have at least 50 people say yes. So N for valid inference is the number of yes must be greater than 5. In this case, it's 50, so we're okay. And the number of no would also have to be greater than 5. In this case, that's 50. We're good. Okay, so that's just the critical value approach there, how we're going to calculate the test statistic. The confidence interval is going to be p hat plus or minus z times the square root of, it's not going to be pH QH over N. That pH was from the hypothesis, and we don't even have to have a hypothesis when we construct a confidence interval. So that's going to be p hat Q hat over N. In this case, that's going to be 0.44 plus or minus, let's say it's a 95% confidence interval, that'd be 1.96. Now it'll be 0.44. 0.56, that's just 1 minus the 0.44. That's the number, or the proportion that said yes in our sample, that's the proportion that didn't say yes, or if there are only two answers, the proportion that said no. And then this would be the sample size. So for this one, is n large enough? It's based on the numbers of yeses in our sample. We've already have that x is 44. So I just meant n valid for inference. The number of yes have to be greater than 5, and the number of no have to be greater than 5. Now this is from the sample, not what we would hypothesize. So this is going to be 44, and this is going to be 56. Anyway, they're both greater than 5, so we're good to go. Okay, now let's just work a couple of problems here to go through these completely. Hopefully by now you have already read the problem. So just reading through here, I can see that I haven't set the marker up. At any rate, I can see that the sample size is 100. I can see that the number of yeses was 42. That means the sample proportion is 42 out of 100, or 0.42. Can we conclude that the population proportion is greater than 0.3? HOP equal to 0.3. Hopefully this is all seeming not that different than what we've already done. We're going to reject HO if z-test is greater than, with alpha 05 and a one-tailed test, that's greater than 1.645. And the z-test is equal to the statistic minus the hypothesized parameter over the standard error. So the statistic was 0.42, the sample proportion, minus the hypothesized parameter, which is 0.3, and divide by 0.3 times 1 minus that, 0.7, over 100, and you should get 2.62, which is greater than 1.645. Therefore, we reject HO and conclude that P is greater than 0.3. Well, that's it for the critical value approach. The p-value approach. Let me go back and say, for this part, was n large enough with p of 0.3 and a sample size of 100, the yeses, number of yeses was equal to 30, or hypothesized to be 30. The number of no's then would have been hypothesized to be 70. So both of those are greater than 5. So this is a valid process to go through. That means that the sampling distribution is a bell curve. That's what that number of yeses and number of no's means. It means we have a large enough sample to guarantee the sampling distribution of p hat to be a bell curve. So we can use the z-table. You may recall earlier in the semester when I was working on the binomial that I showed that if you increased either sample size or the proximity of p to 0.5, it looked like the binomial distribution at small sample sizes was skewed or could be skewed, but at larger sample sizes or closer to 0.5, it looked like a bell curve. This is just the cutoff then for using the z-table. The center of this is 0.3. The statistic we observed was 0.42. That's the specific p hat in this problem. And the z for that is equal to 2.62. So this point right here is 2.62 standard deviations or standard errors above the mean. And if you look that up, you're going to get 4,956. That's here, 4,956. Subtract that from 0.5 and you'll get 0.0044. That is the p-value. Okay, so when you're doing the p-value, one thing you want to do is draw the sampling distribution. You can also do the decision rule. Reject HO if p-value is less than 0.05. It is. 0.0044 is less than 0.05. Therefore, we can reject HO and conclude that P is greater than 0.3, that the population proportion is greater than 0.3. More fully, the information from our sample, that is that we have a sample proportion of 0.42, is sufficient evidence for us to conclude that the population proportion is also greater than 0.43. I'm sorry, greater than 0.3. So then we would have our if-then statement. If P is equal to 0.3, then a 0.0044 chance that our statistic P hat is greater than or equal to 0.42. So there's your if-then statement, which again is just a sentence that describes the sampling distribution that we have here. Okay, now for the confidence interval. Remember we had P hat was equal to 0.42. So we're going to have the statistic plus or minus confidence coefficient times standard error, now using 0.42, and 1 minus that, or 0.58. Divided by 100. Sorry. The formula would have been P hat plus or minus Z times P hat Q hat over N. Got a little bit ahead of myself there. So this would have been 0.42 plus or minus, for 90%, that's 1.645 times 0.42. 0.58, that's just 1 minus the 0.42, divided by 100. And that all comes out to be 0.339 to 0.5011. So if we were comparing it to an HO of P equal to 0.3, or if we were trying to show that P is greater than 0.3, the answer would be yes, the interval is all greater than 0.3. One other thing to mention here, remember in this our x was 42, the number of yes was 42, that's greater than 5. The number of no, if we took a sample of size 100, 42 yeses, 58 no's, that's greater than 5. So we're good to go on making a confidence interval a valid confidence interval. So reading through here, we have a random sample of 150. We have the number of yeses is 84. So p hat then is going to be 84 over 150, and that is 0.56. We want to know if we have enough information to conclude that p is less than 0.6, HO p equal to 0.6. And that's pretty much just reading the problem. I know I'm moving a little fast. If you need to, in fact, what might be a good idea if you're watching this right now is to pause, try to work this problem based on what you just had from number 1, and then come back and watch this. Otherwise, if you're just watching it and I'm moving too fast, of course you can pause as usual. Anyway, we're going to reject HO if Z test, that's less than, so this is less than minus, and so we have 0.5 and one tail, that's 1.645. Just go to the bottom row of the Z table. Z test is equal to the statistic p hat minus the hypothesized proportion divided by standard error. Make sure you use the one based on the hypothesized proportion. So we're going to have 0.56 minus 0.6, sample proportion minus hypothesized proportion, 0.6, 0.4 divided by 150. Now comes out to be minus 1, which is not less than minus 1.645. So we fail to reject HO, and we conclude P could equal 0.6. We certainly can't rule out that possibility. The difference that we observed here could be just sampling error. By the way, on the sample size thing on this, we would take 60% of 150 and 40% of 150. Well, 60% of 150, 0.6, 150 is equal to 90, and 40% of 150 is equal to 60, greater than 5. So we're good to go on the hypothesis test. Sampling distribution. Make sure you get the statistic on the axis there. The center is from our hypothesis, and then we find here p hat is equal to 0.56, and our p-value will be out here. Well, with one standard deviation here, z is equal to minus 1. The area in our table is going to be 0.3413, and 0.5 minus that, because this is the 0.3413. 0.5 minus that is 0.1587. So that's the p-value. So reject HO if p-value is less than 0.05. 1587, that's the p-value, is not less than 0.05. Therefore, you fail to reject HO. P could equal to 0.6. So if I ask you just to do, or if you're doing a decision rule approach using the p-value, it's just reject HO if p-value is less than 0.05. In this case it's not, then the decision is fail to reject HO. P could equal to 0.6. I asked you for the if-then statement, which is really just, if you really want to understand p-value, this statement is what p-value is. You can go all the way back to the coin flipping stuff I've talked about. Flip a coin 10 times, you get 9 heads. That's pretty unlikely if the coin is fair. In this case, if P is equal to 0.6, then there is a p-value probability. And if you did the coin thing, then the p-value would be very small if you had 9 heads. Well, anyway, then there is a p-value probability, 1587, that we get a statistic, in this case p hat, equal to 0.56, whatever we observed, we should say less than or equal, into the same direction as our research hypothesis. So if you ever end up with a p-value that's greater than 0.5, it would be that, you know, we thought it would be less than 0.6, but our sample got us something up here. And now for the confidence interval. The statistic, p hat, plus or minus the confidence coefficient times the standard error when we are doing confidence intervals, or when we don't have to specify a hypothesis. So our p hat was 0.56. Plus or minus for a 90% confidence interval is 1.645 times the standard error 0.56, 0.44 over n. That goes from 0.493 to 0.627. So were we testing this hypothesis? Is it lower than 0.6? Well, maybe not, because it could be as high as 0.627. So 0.6 is in the interval, so P could be 0.6. That's the same thing we had with the other two approaches. Sample size large enough. X was equal to 84. That's the number of yes. That's greater than 5. This is from the sample now, since we're using sample proportion. The number of no would have been 150 minus 84, and so what's that? 66. The number of no would be 66. That's greater than 5, so n is large enough. Be careful on this. We've been doing that 15, 40, 100 stuff. That's for quantitative variables. For qualitative variables, it's the number in each category. In this case, the number of yeses and the number of no's have to be greater than 5. Before I move on to the next topic, for the which is going to be sample size considerations for margin of error, let me just take a moment and I don't have my calculator with me, but I think I can remember the steps here. When you want to check your numbers on this, if you go to Stat, Tests, 1 prop t-test, it will prompt you for a hypothesis. When it does that, you'll put in 0.6. Then it'll ask you for the number of yeses. In this case, that would be 84, and the sample size would be 150. Then it'll ask you for a direction of the hypothesis, which was less than, and then you can calculate and all of that. For a confident, and then that'll give you check figures for your p-value and for your z-test. If you want to do for the confidence interval, you'll do stat, tests, 1, proportion, one proportion Z test up there. One proportion Z interval. I can't remember if it spells it all the way out on that one or not. But if you've already put this other stuff in, then you're good to go. But if not, it'll ask you for X and N and a level of confidence. So you put in the 84, 150, and 90, or 0.9, your choice. And then that'll give you a check figure for this confidence interval, and you can make sure you have that correct. Okay, before I get to the next problems on this, I want to take a minute and just tell you what they're going to be about. And they are given a margin of error. You'll see different symbols for that. Just M, just E, ME. I'm starting to get attached to the MOE, because of the Three Stooges, of course. But anyway, you're given some margin of error. Like you see this in the polls that they report on the news every night now. They'll have such and such percentage in favor of either Romney or Obama or whomever or whatever. They could be asking about some topic as well. But anyway, they might say 035. So when you're dealing with proportions, this is really just the right-hand side of a confidence interval. So if we had that confidence interval of p hat plus or minus Z times the square root of P hat Q hat over N, what we're going to be saying is let the margin of error equal that. So 0.035 equal to Z square root of P hat Q hat over N. And then you have to have, Z comes from your confidence, and P will come maybe from a pilot study or something that you did to get that. Or if you don't have a pilot study or a prior estimate, as I'll say in a minute and show you why, then you can always use 0.5 in there. So when you're estimating proportions, that's the general approach. Of course, we'll work a couple of these here in a minute to obtaining, if you're given this, you have a guess on that, you can just solve for N. We haven't, I'm also going to do sample size considerations from when we do a mean. And we have to use Z on this one because, if you use T, that's going to change all the time and you'll have to do an iterative thing. But when we did confidence intervals, X bar plus or minus Z times sigma divided by the square root of N. So that's our margin of error. So the margin of error, let's say that we wanted a margin of error of 5. That would have to be given. And we want 95% confidence, and we have some estimate of the population proportion, standard deviation, whatever it is, let's say 20. I'm just making something up there. So we would have MOE equal to Z sigma divided by the square root of N. Our MOE is 5. For 95% confidence, that's going to be 1.96. Standard deviation of 20 divided by the square root of N. Then we'll just solve for N. So both of these have the same general procedure. Start with the formula for a confidence interval. The right-hand side, here and here, is the margin of error. So set that equal to the margin of error you desire. So when they're doing these political polls, they might start off saying, well, if we want our margin of error to be 0.035, how large of a sample do we need to take? That's the general approach. Now, I'll admit, in the political polling and stuff they do, they take some other things into consideration. But this is the first basis of it. They'll take into consideration things like making sure they have representation of certain geographic areas or demographic groups or whatever. But anyway, this is the general thing. Set the margin of error equal to the right-hand side of your confidence interval formula. Given a level of confidence and some. In this one, you'll have to know something about what you think the standard deviation is. And in this one, you'll either have to have a pilot study and use that, or you can always do the most conservative thing of all and use 0.5 there. I'll mention that, or I'll show that why in just a second in the context of a problem that we work. I think it's going to be the second problem coming up here, but we'll see when we get there. So I'm going to say on this, if you recognize what kind of problem it is, and in this case, it says how large of a sample, so we're looking to see what the sample size is, and then you just need to make sure you're straight about whether we're estimating means, which this one says, or proportions. So if we were to do a confidence interval for the population mean, it would be of the form x bar plus or minus a confidence coefficient times standard error. This then is the margin of error. Forget the x bar plus or minus. Now you would use that after you collected the data. Margin of error is equal to z sigma divided by the square root of n. So margin of error, we want to be within 25 miles. We want to have 95% confidence. That goes with a z of 1.96. And our standard deviation is 400. So 400 divided by the square root of n. Now normally and it's fine. If you can go from here to the next thing is, I'm going to go ahead and write it here. If you can go from this step to this one, and then calculate it, then you're good to go. I'm going to go through the steps a little more deliberately than that. This should be, by the way, an equal sign. Sorry about that. So if I had that, I'm starting from here. 25 is equal to 1.96, 400 divided by the square root of n. I'm doing this for people that are maybe, if you're really good at algebra, you can skip what I'm doing now and just do the first part over here. So anyway, the first thing I'm going to do is I'm going to multiply both sides by the square root of n. So 25 times the square root of n is equal to 1.96 times 400. Then I'm going to divide both sides by 25. The square root of n is equal to 1.96 times 400 divided by 25. Now I'm going to square everything. So squaring the square root of n will just give you n, and squaring the other side, just take everything over there and square it. And so that's going to give you 983.4. That's the minimum, but you can't take 983.4. And so you want to round up, always round up, because this is the minimum. So you would take 984 or more. Or if you just want to say greater than or equal to 984. Okay, so that's calculating sample size given a certain margin of error, and just going from there. Now, you can see in this case it came out to be 984. Let's say it had come out to be 64. Then you still have to meet the conditions of the central limit there. So if there were extreme values, then you would need to have at least 100 anyway. But if there were not extreme values, I hope I said that right, if there were extreme values, you'd need at least 100. But if you had 64 and you knew there weren't extreme values, even if there were outliers or skew, or if there was skew, you'd still be okay. The 64 would be enough. In other words, that consideration isn't gone. And this is a quantitative variable, so it's 15, 40, 100 again. So now we want to estimate a proportion, and again it says how large of a sample. So I'm going to go ahead and write the formula for a, well, first I'm going to get the marker set up again. Maybe by the end of this semester. Well, probably not, but it'd be nice if by the end of the semester I could remember that every time before I walked over to the screen. Well, anyway, we know when we're estimating proportion and we want to know how large of the sample. When we get around to collecting the data, it's going to be p hat plus or minus z times standard error. So the margin of error is equal to z, the square root of p hat q hat over n. So in this case, it says we want to be within 0.04. That's the margin of error. 90% confidence, that's 1.645. And it says that in a pilot study, 70% said they would travel outside the state for vacation. So our best estimate of P is 0.7. 1 minus that is 0.3. N. Now again, you can do one step here, which I'm going to do. We're going to have 1.645 divided by 0.04 squared times 0.7 times 0.3. And you just put 0.21 there. I'd be okay with that as well. But that's for those of you that are pretty sharp with your algebra and formula manipulation. But I have to say, I always resented it when they made me show every step. But that's just me. And sometimes I, want to show every step anyway because sometimes it's a little more complicated. This one isn't that bad. So anyway, first thing I'm going to do on this one is I want to get rid of that square root sign. I've got too much stuff under there. I'm going to have 0.04 squared is equal to 1.645 squared. And be careful here. You're not squaring the 0.7 and the 0.3. You just take the square root sign away. 0.7, 0.3 divided by n. Multiply both sides by n. 0.04 squared, 1.645 squared times 0.7 times 0.3. I'm sorry, n was what I was doing, multiplying both sides by n. Now divide both sides by 0.04 squared, and you'll have n. It's 1.645 squared over 0.04 squared times 0.7 times 0.3. You can do it like that, but you could also make this further. I guess simplification. I'm going to go ahead and put 2, 1 right there. Well, anyway, that all comes out to be 355.17. That means you need at least 356. Again, always round that up. Hardest thing on this is just recognizing the problem. How large a sample, then make sure you know if you're doing proportion or mean. By the way, the same general procedure would hold for getting sample sizes for difference between two means, or next week difference between two proportions. The math's a little more difficult, and it's not that hard. In fact, I may give you a handout that has those formulas in it, but we won't do that in this class. We would do sample size problems with margin of error only for the one sample cases, for one sample proportion and one sample mean. Okay, part B, similar, but it says we didn't have that prior estimate. So what do we do now? We still have that p hat plus or minus z square root of p hat q hat over n. We still have margin of error is equal to z p hat q hat over n. We still have 0.04 equal to 1.645. So what do we use for p and q? Well, first I'm just going to tell you, use 0.5. If you have no prior estimate, use 0.5. Now I'm going to show you why. If we had p's and q's, whether they're hats or whatever here, if we had 0.1 and 0.9, the product of p hat q hat would be 0.09. Now I'm just going to write down some other possibilities. And you really don't have to do this. I'm just showing you why we do it. And it's because the product of 0.5 and 0.5 is 0.25. And that's the largest product you can get for a P and a Q. So when we use 0.5 and 0.5, we'll always maximize the sample size that we would have to get a desired margin of error and confidence. Now, if you have the prior estimate, you should use it, because if 0.5 is going to be the largest sample size, if you have to do sampling using that 0.7, or if you had 0.8 or whatever, is going to yield a smaller number for n, which means less cost, less time to get the sample. Well, anyway, this is going to equal then, I'm just going to go right to the thing here, and if you have trouble with the algebra, go back and look at the previous calculation that I did. And I'm going to go ahead and make that 0.25. And make sure, one of the, at least math errors I see on this is a lot of time is people want to square that 0.25, or square the 0.5 times 0.5. Anyway, that equals 422.8. Therefore, you need at least 423. Well, that's it for this week's tutorial.